Right, so for number 1, we are given position versus time graphs, and we want to give a brief description of the motion and then use that to sketch the velocity versus time and acceleration versus time. And writing the description can help, because if you look at number 1, it's going up, so that means that it's moving forward, and it's getting steeper, so that means that it's speeding up. So if it's moving forward and speeding up, then I want positive velocities, because forward would be a positive velocity, and speeding up means the velocity is going up, so something like this. And then, if it is speeding up, I do have an acceleration. The fact that this line is going up means it's a positive acceleration. So constant acceleration, it's just positive, so that's above the axis. Now for part B, this is going forward because it's going up, and it's straight, which means it's moving at a constant velocity. So forward is a positive velocity, constant means it's not changing, so that would be my velocity versus time graph. And if it's at a constant velocity, your acceleration is 0. So the acceleration graph has to be at 0. See, the object is moving backwards because it's going down, and as it moves backwards, it's getting steeper, which means it's getting faster. So moving backwards and getting faster. It starts off pretty flat, so I'm going to say that starts at 0 velocity and it becomes more and more negative. That means it's getting faster, just in the negative direction. And the fact that this graph is going down means that there must be a negative acceleration. Now for D, it's going backwards at first and then it's going forward. So at first it's going backwards and it starts steep, but then it flattens out, so it goes backwards slowing. And then it goes forward, getting faster, forward, getting faster. So to show that it's going backwards at first, I want to start with a negative velocity. And then slowing, go to 0, so something like this. That would be a negative velocity slowing to 0. Where it's flat right here, your velocity would be 0, so it starts negative, goes to 0, and then up here it starts positive, and it's getting faster positive, so that will just continue. Now the acceleration is purely, is this have a negative slope or positive slope? This one is going up the entire time, even though it has a negative velocity and then positive. That just means it's going backwards and then forwards. This is going up, so it has a positive acceleration. Part E. This one starts going forward, and then it slows. Forward, slows. And then the second part is going backwards, getting faster. So I start going up. I start with a positive velocity. At the top, the velocity would be 0. And at the end, the velocity would be, oops, that's velocity, would be negative because it's going backwards. So start positive, go to 0, and then continue to become negative. This graph is going down, which means I have a negative acceleration. F is going forward because it's going up, and it is getting flatter, so that means it is slowing down. If it is moving forward and getting slower, I know my velocity is positive because it's going forward, but the velocity is going to 0, so it would look something like this. I start with some velocity and it goes to 0, goes to a stop, and then because this is going down, my acceleration is negative. G, I am moving backwards, getting flatter, so that means it's going backwards and getting slower. Lower. So I start with some negative velocity and I end at like flat or 0, so start negative, end at 0. And then because this is going up, that would be a positive acceleration. That should be flat, by the way. And then H is going backwards at a constant velocity, so I need a constant velocity graph, but it needs to be negative because it's going backwards, and because it's constant velocity, there's no acceleration. So acceleration is 0. Now the next question asks, in which of the cases above are the velocity and the acceleration in the same direction? So that could be positive velocity and positive acceleration, or negative velocity and negative acceleration, and there's an example of both. So here I have positive velocities and positive acceleration. They're both above on the graph. So an example of positive V and positive A would be part A, or graph A, I guess. And then negative velocity and negative acceleration would be graph C, because this is below the axis and below the axis. And in both of these cases, A and C, they were speeding up. This one was speeding up as it goes forward, positive, positive. This one was speeding up or getting faster as it went backwards, negative and negative. When are they opposite directions? So opposite direction would be F and G, because F has a positive velocity but a negative acceleration. G has a negative velocity and a positive acceleration. So F and G are both opposite opposite direction for velocity and acceleration. And in this case, they slow down, whereas in this case, these two speed up. Which makes sense because if velocity and acceleration are in the same way, they speed up, and if they're opposite, they slow down. Because they're going to zero, so slowing down. Okay. Multiple choice, I guess it's not multiple choice yet. So here we have a velocity versus time graph. So in this part, this is constant velocity forward, and this is slowing down. Either way, it's going forward the whole time. So I want to know at which time it's at the maximum displacement. Displacement is like how far away you are from your starting. Well, if I go forward and then I continue going forward just at a slower rate, I'm still moving forward, so the maximum displacement would actually be at 4, because I'm moving forward the entire time. So at 4 seconds. And to find the maximum displacement, well, I have velocity and I have time. You would multiply velocity times time in order to get delta x. That means area under the graph. And then finding area under the graph is pretty easy. You can break it up into this square, which was, I guess it's a rectangle, 2 times 4, which is 8. And then this triangle, which has a base of 2 and a height of 4. So base times height divided by 2 gives me just 4. So the first 2 meters you walk, or first 2 seconds you walk 8 meters, and the next 2 you walk another 4. So the displacement was 12 meters at the end at 4 seconds. Number 3, so we have a x, or position versus time graph, and we are looking for where the speed is the highest. So it gave me a hint, do not confuse speed with the velocity. For speed, you don't care about direction. So don't care if it's positive or negative, just which is faster. So if you look, if it's staying at the 4 meter mark, because this is position, that means it's at rest. This would be moving forward, and this would be moving backwards. I don't care whether forward or backward, I just care about faster. And this section would be faster because it's steeper. It's closer to the vertical. Section 2 is not as steep, so it's not going as fast, even though it's forward. And when did, or during which intervals did the velocity remain constant? Well, here it's a constant velocity of 0. This section, it's got a constant velocity, not 0, but still a constant velocity because it's straight. And then the third one, I again have a constant velocity because it's straight. So I have 3 different constant velocities. So in each of the 3 intervals, I have a constant velocity. It changes between intervals, but it's not changing within the interval. Instantaneous velocity at 7 seconds. So 7 seconds is somewhere in here. I can't find velocity of a point, but I can find it for a section. So velocity is change in x over time from 8 meters down to -4. It goes down 12 meters. And from, I think it's, let's see, 5 to 8 seconds, it takes 3 seconds. So then your speed, or your velocity, is -4 meters per second, and you need the negative because it is going down. Or you can think about that as like the backwards direction. It's the same thing. Which of the following set of graphs represents the same motion? So what I did is I looked at just the first piece through each of them. So this one is straight going up, which means for a position graph or displacement graph, that's constant velocity. Now here, it was constant velocity, or sorry, it was a velocity graph and it goes straight up. That means that it's increasing in velocity, which means it's getting faster. Here, it was flat, which means constant, and it was acceleration, it was constant, so constant acceleration. So the constant acceleration and increasing velocity makes sense because this was a positive acceleration, so it makes sense the velocity graph would go up. This does not make sense because this was straight, going at a constant velocity, does not make sense. If it was increasing velocity, it should have been getting steeper. It should have looked something like this. So 1 does not match, but these 2 do match. So it was 2 and 3, which is B. Number 7, I want the acceleration graph of speeding up, cruising at a constant velocity, and slowing down. So at a constant velocity, your acceleration has to be 0. So the only one that had acceleration of 0 in between stuff was A. It had this section right here. And then you can still obviously check. So if it's speeding up, I have a positive acceleration. And then when it was slowing down, I had a negative acceleration. And then when it stops, I obviously have 0 acceleration, so I'm back to 0. So this checks out. Number 8, I want the final displacement as described in this VT graph, so that's at the very end. So the first part, to find area under the curve, because this is a velocity graph. So this green part would be the distance it goes forward, and then this blue part would be the distance it goes backwards. And I'm always trying to go from the graph to the axis, so in this case it actually is under, you go down. Whereas this case, you go up to the axis. I don't want to go sideways. It's always from the graph to the axis. So here, because this is a velocity versus time graph and it's asking for displacement, that's just area under the curve. You can actually sit and calculate this. So you can break it up into your like rectangle and this triangle and this triangle. You get the total is going to be like 11.875. But you also can look, and these two are the exact same shape, so I'm going to get a negative 11.875. And without calculating, just looking and be like, oh, it's the same numbers, the same shape, you know your displacement is going to be 0 because it goes forward and backwards the same amount. So however many meters I go forward, if I go backwards that many meters, I end up back where I started, 0 displacement. 9 is asking for the magnitude. Magnitude means you don't care about sign. So the magnitude of the average acceleration during the 3 sections. So you could just look velocity versus time. The acceleration is the slope of a VT graph. So you can look, so steepest to less steep. And this would be the steepest, then this, and then obviously flat is the least steep. Or you can actually calculate, so the velocity, change in velocity over time, this changes by 10 in 5 seconds, so that is acceleration of 2 meters per second squared. This is at a constant velocity, so 0 acceleration. And this changes 10 to 5 by 5 in 10 seconds, so it's negative 0.5. But we are talking about magnitude, so we don't really care about the sign. It's just the most acceleration to least without positive or negative. So the most was A. And then C, and B would actually be the least because it has none. And none is less than this if you don't care about sign. So D, ACB. Number 9, we have a velocity versus time graph. And it says an initial position at 10 meters. So at time is 0, it was already at the 10 meter mark. The position after 2 seconds, well, you just use area under the curve. And base times height over 2, you get 5 meters. That means that it moved 5 meters. If it was at the 10 meter mark and their delta x is 5 meters, then now, after 2 seconds, it's at the 15 meter mark. And then after 6 seconds. So go to 6 seconds, that's continuing here. I broke it up into a triangle and a rectangle. This was 6, this was 8, which means in here it walked another 14 meters. So you could say the 15 plus another 14 gives me 29 meters. Or you could say now it's walked a total of 19 and just add that on to the beginning. 10 plus 19, you still get 29 meters, either way. And then position after 9 seconds. So position after 9 seconds. You would need to find the area under this curve. This is below the graph, which means that it's going backwards here or in the negative direction. So when you do base times height over 2 and you get the 3, that's actually a negative 3 right there. So now I was at 29 right here, and then I go back 3 meters, so now I'm at 26 meters after 9 seconds. And then you could go through, and your total displacement in here is 16 plus the 10 at the beginning, so 26. It's the same either way. Number 10, so a train is moving, and this shows the position versus time graph. Well, it's curved, which means it's not at a constant velocity, so you can cross off D. And it is getting flatter, not steeper. So the fact that it gets flatter means that it's getting slower, so it slows down the whole time. A lot of people that miss this put C, because they said speed up and then slow down. If it was speeding up, it would get steeper. At no point does it get steeper. It's constantly getting flatter. If it was getting steeper and then flatter, it would look something like this. So getting steeper here, and then it turns and gets flatter, but that's not what happens, so it's B, slows down the whole time. Between 3 and 9 seconds, so go to 3, go to 9, so I'm looking for how far it moved. this is the distance. So if it's 50 meters away and now it's 400 meters away, then from then to then, it moved 350 meters. And then average speed is just the change in x over time. Change in x, we just said how far it moved, would be 350. And from 3 to 9 seconds, that's 6 seconds that have passed. So then your average speed would be 58.33 meters per second. Number 12, so during the first 8 seconds, we have first of all, we have a velocity versus time graph, and we were talking about accelerations. That's just the slope of a VT graph. So if you look, these two have the same slope. It's just that this one has a negative slope and this one has a positive slope. So they're equal in magnitude, meaning it's like the same, it's just opposite in sign. One's positive, one's negative. At 14 seconds, which object is moving faster? So I'm going to go up to 14 seconds. So I have a position versus time graph. So the faster just means steeper. So if I look at 14 seconds, object 2 is the steeper one. And which one is ahead of the other? Object 1, because it has a higher position. Higher position means it's ahead of me, does not mean faster. The faster is determined by the steepness of the position graph, and object 2 would be steeper. We've got another velocity versus time graph, and it's starting from the origin at x equals 0, so I don't have to worry about some initial position. I'm looking for the time that the car is farthest from the origin. So let's break this up, because I have 2 parts to this graph. I have one part where it's going forward right there, and then I have a second part right here where I have a negative velocity, which means that it's going backwards. And it ends up going forward more than it goes up backwards because this is a bigger area. So if I want to know when it's farthest from the origin, farthest from when it starts, well, I just look at the graph. If I'm going forward this entire time and then I start to go backwards, and I don't even go backwards as much as I went forward, so you go forward for a really long time and then you turn around and go backwards some, well, I'm farthest at that point right before I turned around and went backwards, which is between positive and negative velocities, and that was at time is 5 seconds. Finding the average velocity, well, average velocity is just displacement over time. Time is easy. I'm asking for the entire 10-second interval, but finding the displacement is where you have to actually go through and calculate. So I broke it up into this rectangle and this triangle. This was 6 times 4, which is 24, and then 2 times 6 divided by 2, no, times 4 divided by 2, which is 8. And then here I did the same thing. This was 16, but backwards, so I'm going to put negative 16. And then right here was negative 2. So then you add it all up, 24 plus 8 plus negative 2 plus negative 16. My displacement was 14 meters. And then you just do 14 meters over 10 seconds and you get the 1.4. Now in order to decide between A and B, you would have to actually do all of this math and calculate it. But looking at the graph, you could definitely have crossed off D, because I'm going at 6 meters per second for a solid amount of time. And then you're going at -4 for a decent amount of time as well. So there's no way 6 and -4 would average out to +5. And then same with the +3. They're not exactly even, but if you were to do the 6 plus -4 divided by 2 to average it, you would get -2 over 2, which is close to 1. So that's how I'm between A and B. And it's not exactly 1 because they're not doing the same velocity for the same amount of time. It's actually -4 for a little bit longer than it was at +6. But you can cross off C and D because those are definitely too big. All right, our equation practice, what everybody hated. We have a swimmer in a relay, and it has a 0.5 second lead, and is swimming at a constant speed of 4 meters per second. So this is my pool. It says there's 15 meters to go, and she's going at 4 meters per second. And then another swimmer moves in the same direction. What speed do they have to go at in order to catch up? So what I would do is I would plug in V is delta x over t, because we're talking about constant speed, no acceleration. So this is my constant speed equation. The velocity of the first swimmer was 4. They moved 50 meters. And then I would use this to find time. So multiply t up and divide over. You would get the time that's needed is 12.5 seconds. Yes. They would need 12.5 seconds. And this person gets a 0.5 second head start. So if they go at 0.5 seconds, how fast does this girl need to go in order to catch up? Well, if they take 12.5 and have a 0.5 second lead, then this girl has to do it at 12 seconds. So they need to do it in 12 seconds so that at the end they've caught up. Her in 12.5, her 0.5 head start, her in 12. And now you just calculate. Velocity is displacement over time. So 50 meters, because it's still the same pool, but now in 12 seconds gives me a velocity of 4.167. And it should make sense that she would have to go a little bit faster than the other one in order to catch up. If you were to add and do 13, you would get a slower speed, which doesn't make sense. Right, number 2, how long does it take an automobile traveling 60 meters per second to become even with a car that is traveling at 40 meters per second if they are initially 125 meters apart? So this is 2 cars, I'm going to call it A and B, going at 60, and then this one going at 40, and they originally had 125 meters apart, and at some point he's going to go fast enough to catch up. So I want them to end up in the same spot. So your first equation, because it's going at constant velocity, would be the velocity is displacement over time for A guy, A. And his velocity would be 60 is displacement for A over time. And then B would be 40 is displacement for A or B over time. And I want them to end in the same spot. I don't necessarily want their displacements to be the same. If you think about it, you want 60, this guy, A, you want him to go as far as this guy does, plus this extra 125 meters. So if I were to rearrange for displacement, 60t is the displacement for A, and then 40t is the displacement for B. And you want the displacement for A to be equal to B, but also plus the 125. So 60t is equal to 40t plus the 125. And now you've set up, you want them to end in the same spot. So he needs to go this guy's distance plus the starting. Now you just subtract over, 20t is equal to 125, and divide over, and your time is 6.25 seconds. And then you can always plug in like 60 times 6.25, 40 times 6.25, and then add 125 in, and they would be at the same position. Number 3. So runner A is initially 6 kilometers west. I meant that to be a meter, by the way. That was a typo. 6 meters west of a flagpole, running with a constant velocity of 9 meters per second due east. So if this is my flagpole, and I am 6 to the west, so you can think about this as like negative 6 meters, and they are going at a constant velocity of 9 meters per second to the right or east. Runner B is initially 5 meters east, so like a positive 5 away from this flagpole. This flagpole is like position 0, and they are going 8 meters per second west. So I am trying to find when they are at the same position and what that position is. So what I would do is I'd say, okay, call this A and this one B. Their position or their velocity equation would be V is delta x over t, your 9 is your delta x over the time it takes, whereas his would, and it would be negative 9 because it's going in, nope, that's positive 9, this would be negative 8, sorry. And this would be negative 8 is delta x over t, like this. Now I don't necessarily want their displacements to be the same, but I want this guy to, well, how do I explain this? So this displacement would be 9t is delta x, and this would be negative 8t is delta x for the B. I don't necessarily want their displacements to be the same. I want this 6 meters plus how far he goes, and this 5 meters plus how far he goes to be equal. Because I want their displacement plus like how far away they started. So their 9t minus 6 is equal to the negative 8t plus 5. And now I just set these equal and solve. Add the 8 over, you get 17t. Add the 6 over, you get 11. So t is equal to 0.65. Now that's the time when their positions are equal or when they meet. But I asked what their position is, how far away it is from the flagpole. And I have an equation for what that position is. So I can just plug in the 9t minus 6, and when you plug that into your calculator, you get negative 0.176. You also can plug into the negative t plus 5. You should get the exact same answer. Oops, sorry. You should get the exact same answer, so that is your position after that time. And the negative just means that it's in the negative direction, or west, so it was 0.176 meters west of the flagpole. So this is super similar to what we did on the last one, where we found the displacement and just added in like that initial position to set them equal. 4, an apple falls from a tree and it hits the ground with a speed of 5 meters per second. Well, if it just falls, right, if it's just dropped, the initial velocity would be 0. Your final velocity, or your v, after some time would be 5. Your acceleration is negative 9.8, and you were looking for the height, so delta y. So I would use the v squared equals v naught squared plus 2 acceleration delta y, in this case, not delta x. And then 5 squared equals 0 squared plus 2 times negative 9.8 delta y. That's 25 is 19.6 delta y. You divide over, you get 1.2. Number 5, the car is traveling with a velocity of 22 meters per second and it accelerates uniformly at 1.6 meters per second squared for 6.8 seconds. What is the velocity after? That was a typo. That was supposed to be 6.8. After that time, and how far has it moved in this time? So this is my initial velocity. This is my acceleration. This is my time. I'm looking for velocity after. So that's just v is v naught plus at. 22 plus 1.6 times 6.8. And I get 22 plus 1.6 times 6.8. You get 32.88 is your velocity after that time. And then I also want to know how far it moved. So that's like your delta x. V naught t plus 1/2 at squared. V naught was 22, time was 6.8, 1/2 acceleration of 1.6 times 6.8 squared. And plug in. You get 186.592 meters as your displacement. So that would be the velocity after and how far it travels in that time. For this one, you actually could use the last equation as well. It's the same thing, it's just a tiny bit more work to solve for delta x, whereas this is already solved. Okay, number 6, a motorist is traveling at 35 meters per second and encounters a deer in the road 200 meters ahead. If the maximum acceleration that the brakes are capable of are negative 9 meters per second squared, what is the maximum reaction time of the motorist that will allow him to avoid hitting the deer? Okay, so it helps to draw a picture. You've got a motorist going at 35 meters per second, and there is a deer 200 meters away. This is the deer 200 meters away. And the car has a deceleration of negative 9 meters per second. What is the maximum reaction time that he can have in order to avoid hitting the deer? So what I would do is I would say, okay, let's make our knowns. Initial velocity is 35. Acceleration is negative 9. And if it goes to a stop, then the final velocity is 0. So what I would use is this, and then find how far is needed for the car to stop. So it says 200 meters away. 200 meters is how far away the deer is. I already know the acceleration, so let's find how long is needed for the car to brake. So you would plug into the v squared, v naught squared plus 2a delta x. So 0 squared is 35 squared plus 2 times negative 9 delta x. 35 squared, that's negative 18 delta x. That becomes negative 1225, divide over, and you get that your delta x is 68.06 meters. So that's the distance that the car needs in order to brake. So the 200 is actually way more than that. So they only need 68 meters to hit their brakes. Once they hit their brakes here, then they would stop right in front of. So they have, and you can just subtract, they have 131.94 meters to go before they have to brake. Before they're braking, they're traveling at a constant velocity of 35, so you would just use v is delta x over time. velocity of 35 because I'm not accelerating yet. That's when I hit the brakes, which I only need this distance. So the time that I would take to go this distance, multiply up, divide over, and the time needed would be 3.77 seconds. So I could go at this constant velocity of 35 meters per second for this long before I would have to hit the brakes with this deceleration to stop just in front of the deer. Okay, so I broke it up into a constant velocity right here before the brakes and then the acceleration with the brakes in the second part. Now part B is saying if his reaction time is instead 3.95, well, let's look. That's more than the maximum, so that means that he is going to hit the deer because he's spending way too much time before he even tries to start stopping. How fast will he be traveling when he hits the deer? So he's still coming at 35 meters per second. The deer is still 200 meters away. If he's going at 35 meters per second for this time before he brakes, then that's constant velocity. V is delta x over t. Velocity of 35, looking for how far he would go before he even hits the brakes. The time, oopsies. Oh no. Whew. The time that it takes, well, I gave you how long he took to brake. So you just multiply up, and the displacement before he even hits the brake, just when he's going at a constant velocity, was 138.59. So that's how far he travels before he even touches the brakes. So the distance between him and the deer when he starts to brake is just, subtract from 200, 61.4. So this is his distance between him and the deer while he's braking. His initial velocity is 35, it's right before he starts to brake. Acceleration is -9. His velocity would not be 0 because that is not enough distance for him to brake in. But I know that the distance until he hits the deer is 61.4, and I want to know the velocity he would be going at before he hits the deer. So that's the last equation. The v squared is what I'm looking for. 35 squared plus 2 times -9 times 61.4. And this is how I know everyone copied my key, because I accidentally left off the negative sign in my calculator when I did it, and everyone had the same mistake. So you get v squared is 119.8, and then you just square root, and you get your velocity is 10.95 meters per second. So that would be the velocity that he hits the deer with if he was going at this speed for the reaction time of 3.95, because he would have this distance until he hits the deer, so find the velocity after that distance. Okay. Oh. So the next one, we have a bunch of data for displacement and time. That's like your delta x and t. And I'm looking for acceleration. And it doesn't say explicitly, but it was started from rest. It wasn't pushed down. So I'm going to use that v naught is 0, and then use this equation, second equation. And you can actually use any point. I just picked the last point because you don't need to do it like 6 times. So I use the 1 meter, 0t, 1/2, and your acceleration is what you're looking for. And then t is 1.52 squared. So then 1/2 of 1.52 squared, that's 1.1552a. And then you just divide over, and you get your acceleration is 0.866 meters per second squared. 8, give an expression for the fastest velocity a car can be moving in order to stop within distance d and deceleration a. So if it goes to stop, final velocity is 0. Your delta x is just d, and your acceleration we're just calling a. And we are looking for the velocity you can be moving at the beginning in order to stop within that distance with that a. So that is your last equation. 2a delta x. 0 squared equals v naught squared plus 2ad. Now I just subtract over. So v naught squared is -2ad. And then v naught is the square root of -2ad. And if you're sitting there like, wait, you can't take a square root of a negative, this doesn't necessarily have to be a negative number. In fact, if you're slowing down, that would be a negative acceleration, and the negatives cancel out, so you can take the square root. Number 9. A particle begins from rest at 10 meters from the origin at time equals 0, and it begins accelerating at a constant 2 meters per second squared in the negative direction. And then at t equals 4, the particle reaches a certain speed, it stops accelerating and continues at that speed until 7 seconds. What is the position at 7 seconds? So I'm going to break it up from 0 to 4 seconds where it's accelerating, and then 4 to 7 when it's at a constant velocity. From 0 to 4, the x naught, or your initial position, is 10. The initial velocity is at rest, so 0. Your acceleration is -2, and the time is obviously 4 seconds. And I'm looking for the position after that. So x is x naught plus v naught t plus 1/2 et squared. So that's 10 plus 0t, which goes away, plus 1/2 -2, 4 squared. So 10 plus 0.5 squared. That gives me my position is -6 meters at the t is 4 second mark. Oops. So now my position is -6 meters after 4 seconds. It says after the 4 seconds that the particle has reached a certain speed and stops accelerating and continues at that speed until 7 seconds. So from 4 to 7 seconds, that's 3 seconds. And velocity is delta x over t because it's moving at a constant velocity. I want to know how far it travels in this time, because that means I need to know what the velocity it is. Well, it started from rest, but then it accelerated for 4 seconds. So let's just plug in and do v is v naught plus at. The velocity at the beginning was at rest. Acceleration -2 times 4. That means the velocity at the end of 4 seconds was -8 meters per second, which would then be my velocity for the next part, because that's when it stops accelerating. Now you just multiply up. Delta x would be -24 meters. So if I'm at -6 and I go another -24 meters, now I'm at -30 meters, which is my answer, B. And now I'm done. Thank God.
Red line right on the side, or right on the back. Sorry.
Okay, I'll let you do that.